In the previous episode, we covered the theory, applications, and limitations of the rational and modified rational methods. In this video, we move directly to problem solving. Here, the focus is on correct application, parameter selection, and avoiding common mistakes. If you want to apply these methods with more confidence, this video is essential. Let's get started. In our first example, we want to use the rational method to calculate the 100-year ARI peak flow for a 25-hectare semi-urbanized catchment with an estimated time of concentration of 15 minutes. The fraction impervious in this catchment is 0.6, and the IDF table for this site is also available. Different guidelines may use different methodologies to calculate the runoff coefficient using the fraction impervious. In this example, we use Australian Rainfall and Runoff Guidelines 1987. Based on this, C10, the runoff coefficient corresponding to a 10-year ARI event, can be found by this formula. Here, C10 pervious is the 10-year ARI runoff coefficient for pervious surfaces. In this example, this value is provided as 0.1. Using this formula, we can calculate 10-year ARI runoff coefficient as this. The answer will be 0.58. Then we need to adjust the runoff coefficient for 100-year ARI. For this, the AR&R guidelines suggest multiplying suitable frequency factors using the below table. As you can see, the frequency factor for 100-year ARI is 1.2, so we can adjust the runoff coefficient like this. C100 is equal to C10 multiplied to 1.2, which will be 0.696. Please note that the outcome of this adjustment cannot go beyond 1. Then we refer to the IDF table to pick our rainfall intensity. For rainfall duration equal to the time of concentration of 15 minutes and the frequency of 100-year ARI, the rainfall intensity is 110 mm per hour. Now we are ready to apply rational formula and calculate the peak flow. The peak flow will be 5.317 cubic meter per second. If you want to extend this to the modified rational method, the synthetic triangular hydrograph will be like this. We can also estimate the runoff volume by calculating the area under this synthetic hydrograph. The volume will be 15 times 60, converting minute to seconds, multiplied to 5.317 our Q peak, which will give us 4,785.3 cubic meter. In our second example, we have two catchments draining to point A. The objective here is to estimate the 1% AEP peak flow at this point. A common mistake is to assume that peak flow at point A is the summation of the individual peak flows Q1 and Q2. In fact, QA is always smaller than Q1 plus Q2. The right approach is to treat this as a single catchment with two sub-catchments. First, we need to find the longest time of concentration to the outlet A. Based on the given information, the longest TC of 15 minutes from catchment 2 is going to be selected. Assuming rainfall duration of 15 minutes, we pick the rainfall intensity for 1% AEP from the IDF table. That will give us 113 mm per hour. Then we find the overall catchment area, A equal to A1 plus A2, that gives us 35 hectares. In the next step, we will find overall runoff coefficient using the weighted average formula like this. That will give us the runoff coefficient of 0.543. Finally, we substitute values in the rational formula to get the peak flow at point A. That will give us Q of 5.965 cubic meter per second. We can now compare this with the summation of Q1 and Q2. For catchment 1, TC is 10 minutes and give us the rainfall intensity of 138 mm per hour. So the peak Q1 will be calculated like this. For catchment 2, the time of concentration is 15 minutes and that will give us the rainfall intensity of 113 mm per hour. So the peak flow will be calculated like this. As you can see, the calculated peak of 5.965 cubic meter per second at point A is smaller than the summation of Q1 and Q2. In the third example, we have a 30-hectare catchment with a pre-development 1% runoff coefficient of 0.3. Based on the development plans for this catchment, the 1% AP post-development runoff coefficient will increase to 0.7. The catchment time of concentration is assumed to be 15 minutes. Here, we aim to use the modified rational method to identify the critical storm for a detention basin intended to mitigate development impacts on peak flow and to reduce peak flow to pre-development levels. As we learned in episode 1, the modified rational method assumes a triangular hydrograph for rainfall duration equal to Tc. while the shape becomes trapezoidal when D becomes larger than TC. By increasing the duration, intensity reduces and therefore peak flow QD will also decrease. Assuming a peak outflow of QA for the basin, the storage volume is the area between the inflow and outflow hydrographs when the inflow exceeds the outflow. Here we draw a horizontal line at QA until it intersects the inflow recessing limb, yielding the triangular outflow. The shaded area shown here is the storage volume, calculated using this formula. In the first step, we calculate outflow QA using the rational formula. For the given TC of 15 minutes, the 1% AEP rainfall intensity from the IDF table is going to be equal to 113 mm per hour. Substituting this in the rational formula, we get this. In step 2, we find the critical storm duration. In this process, we need to try several rainfall durations and identify the one that maximizes the storage volume ST. Since this is an iterative process, it is easier to use Excel. Well, I have set up the Excel spreadsheet here. The 3 constant values that I'm going to use are listed here. The runoff coefficient for post-development scenario, which was given as 0.7, catchment area of 30 hectares, and time of concentration of 15 minutes. The first 2 columns of our calculations here are the duration and the intensity. For duration, basically, we need to have a couple of durations. Generally, we start with something smaller than the time of concentration. Here, I have chosen only 10 minutes, as you can see. But for the larger durations, we generally go for a couple of options. And here I have gone all the way to 120 minutes, 2 hours. I believe that would be sufficient. So later, if our calculations show that we need to extend these durations for something larger, I can add that to the table. The intensity values here for the 1% AEP come from the IDF table. So I've already picked up the values equivalent to different durations, for example, for 10 minutes, 15 minutes, and so on, and are listed here for our calculation. The inflow QD is going to be calculated using the rational formula here, 1/360 CIA. So I'm going to start that. So the first thing is I'm going to pick up the C, and for that one I'm going to add $sign to fix the position, and then multiply that to the catchment area. Similarly, I need to fix that one as well because I'm going to drag it later. Okay, let me fix that. And then finally, we have the rainfall intensity here. So multiply to rainfall intensity, which is available in this cell. And at the end, I'm going to divide it to 360, which is for the unit conversion. And the answer is going to be 8.050. And I'm going to copy that all the way down here. So as you can see, by increasing the rainfall duration, because our intensity decreases, our QD is also decreasing. So from 8, it goes all the way down to 1.5. Something that I need to highlight is that previously we have calculated QA, and that remains fixed in our calculation. So 2.825 that I just calculated a few minutes ago is going to be fixed here. Another important point is that generally we don't expect our calculation be valid when our QD is getting smaller than our QA. And the reason is here because of the geometry that we explained earlier. As we explained, QA is going to be drawn as a horizontal line, and then that will touch the recessing limb of the inflow hydrograph. So practically, for having area of hydrograph which the inflow exceeds the outflow, we need QD be larger than QA. So our desired shape is like this. So the blue shaded area is going to be the ST that I'm going to calculate. So therefore, I would say that the last 3 rows of the values that I have here are not going to be valid in my calculation because QD is getting smaller than QA. So I'm not going to use that one. So coming to the inflow volume, the inflow volume is practically the area under the trapezoid that QD is the peak of that. In other words, that the first term of the ST. QD multiplied to D gives me the area under the whole trapezoid. So it's very simple. I have my QD ready, and that will be multiplied to the duration. The only thing you need to be careful about is the conversion, because cubic meter per second need to be multiplied to seconds. So I need to multiply the duration of minute into 60 to get it as seconds. And after that, I'm just simply copy that all the way to here as we discussed, because the other ones are not important for me. So for the outflow, I'm practically calculating the second term of the ST, which is going to be the area under this red triangle. As you can see, the peak of it is QA, the base of the triangle is D plus TC. So the calculation is going to be like this. So I'm doing that. So that will be QA multiplied to the summation of the duration and our TC. I can just type 15 here because the TC is fixed. I multiply that to 60 for conversion and then divide it by 2. And I need to copy that all the way to this point. And finally, our storage is simple. Is just simply the inflow minus outflow. And I copy that as well. So my target is basically the maximum ST, and as you can see, the maximum happens here. I give it a color, and that's for the 30 minutes duration. In other words, the critical storm duration for this detention basin is basically 30 minutes, means that this is the time that we need the largest capacity or largest volume in order to meet the requirement of reducing the inflow peak into the outflow peak. In other words, here the target was reducing the peak of 4.311 to peak of 2.825. And for that one, that's what I need. That's the required volume. As you saw, these examples illustrated how the rational and modified rational methods are applied in practice. Accurate results depend on correct assumptions, parameter selection, and interpretation of outputs. If this video was helpful, please consider sharing it and subscribing to the channel for more videos like this. Thank you for watching, and I look forward to seeing you in the next one.